iC-Haus. Integrated Circuits.
Good morning, good day, good afternoon. Welcome to our laser webinar today. My name is Patrick Stahl. I'm your moderator, and with me are our laser experts Uwe Malzahn and Stefan Kraus. You cannot see Stefan at the moment, but you will meet him later on during the webinar. Our topic today is going to be direct time of flight distant measurements with iC-HS. Before we get started, I'd like to take a moment and introduce the webinar tool to you. So this is the control panel here. With this little red arrow, you can open and close the control panel. And here's the questions section, very important section. We want you to ask questions, so please post your questions here. They will be forwarded to our technical team and answered in a Q&A session after the webinar. Then we have here the screen. On the top screen, you see the speaker. On the bottom screen is the presentation. You can use this little handle here to adjust the size of each section, but please be careful. Don't pull it up too much, because then you close the speaker section and it might be difficult to get back again. So without further ado, I'd like to hand over to our laser experts, Uwe and Stefan here. You will talk you through the iC-HS.
Hello and welcome to our second webinar featuring the ultra-short pulse laser diode drivers of the iC-HS family. Today we want to have a closer look on how to use these drivers in a direct time of flight distance measurement. In our last webinar, we already introduced a number of exciting applications benefiting from the short gain switching spikes enabled by the iC-HS drivers. We also identified the distance measurement, in particular the direct time of flight distance measurement, as one of the core applications of interest for the iC-HS drivers. This is why today we want to have a closer look on how to put such a direct time of flight distance measurement into practice using the iC-HS. A short recap on how direct time of flight works. The idea is to literally measure the time it takes the short laser pulse to travel from the laser diode to the target and back to the sensor. This time is measured, for instance, by a time to digital converter. And from this measured time, one can easily calculate the distance to the target. This is why this measurement principle is commonly referred to as the stopwatch principle. It shows no ambiguity, but requires quite short laser pulses. So why is the iC-HS in particular suited for these type of applications? Well, it features a non-chip short pulse generator. It is capable of driving up to 500 milliamps of laser diode current. It features a synchronization output to start the stopwatch, an energy limitation to support safety concepts, and all these functions are fully digitally controllable via an SPI or I2C interface. Our laser toolkit presents an almost plug-and-play construction kit for testing these type of drivers. So, in our today's demonstration, we're using from this toolkit the high-speed module HS3M, our host adapter HG2D to easily operate the high-speed module and to easily mount it onto an optical stage, for instance. We'll also be using the oscillator IC213 to trigger the laser pulses, and we're using the sampling oscilloscope IC227 to visualize and monitor the short laser pulses. So what we have prepared here is a lab scale direct time of flight measurement, and we're going to discuss the key components used and the design requirements for these components. So to this end, I give you our laser applications expert, Stefan Kraus.
Greetings, dear audience. My name is Stefan Kraus. I am a laser application expert here at iC-Haus. I am going to talk you through the key components that we have chosen for this setup. And as Uwe already introduced, the iC-HS is capable of being our laser source with very short pulses and the synchronization output to trigger the starting point of our stopwatch. So what we also need is something that can trigger the stop point in time of our stopwatch. And for this, the obvious possibilities are single photon avalanche diodes or very fast convenient photodiodes. The so-called SPADs, single photon avalanche diodes, have the big advantage that they are super sensitive. Even a single photon can trigger its output signal. But then you have always to consider, was it really triggered by the laser pulse we sent out? Or was the event triggered by anything else, like ambient light, for example? Also, it's not completely clear if the photon that triggered the SPAD was part of the beginning time of the pulse, the middle, or if it was sent out at the end of the pulse. So this is why the very short pulses reduces the ambiguity quite a lot, and that is why we go for the gain switching pulse of a laser diode. And for all this, we need quite complex post-processing when single photon avalanche diodes are used. As we want to have an easy setup here, we are going for the very fast conventional photodiode. With this, we cannot go to the extreme length because of the sensitivity. But with this diode that we chose, which is rated for 10 gigabit per second data connections, there are roughly 100 picoseconds allotted for each bit in the data stream. So this is well suited to resolve our 100 picosecond, 200 picosecond in this region gain switching pulses. And from that on, we can more easily go about the post-processing. Next is our time-to-digital converter, TDC. In our experimental setup here, we have ranges from a few centimeters to about 1 meter in distance. If we want about 1 centimeter of accuracy, we can use this to check out what the accuracy of the time-to-digital converter needs to be. Light travels very fast. 1 centimeter is traveled in about 33 picoseconds. And there are quite several TDC concepts on the market which fulfill this accuracy requirement. We opted for one that is about 20 picoseconds in accuracy and also features differential inputs, which make our laboratory setup way more robust, as we then can have the time-to-digital converter on a separate circuit board and then just connect it with normal wires and have not to implement it on a chip or even on a PCB with our own chips. All those 3 parts would be enough for the distance measurement derived from the time measurement, But there's one additional item that we added. This is our 11 gigahertz sampling oscilloscope, which then can give us the pulse form because of the fast photodiode. This is very convenient when we later want to find the best configuration in terms of electrical pull pulse lengths for the iC-HS, and in general a very good tool to analyze the profile of a beam. So let's go to the live demonstration. Maybe it's now time to enlarge a bit your screen with the speaker and the camera, as we will go back to the presentation in a few moments. So right here to your left-hand side, we have our laser source. As this is mainly not visible behind the one optic that collimates our laser beam, I have brought the standalone board with me. Maybe you can have a look here. And the camera now zooms in, and I try my best holding it in a good angle to the camera and the light. You can see that we have a little black piece on the high-speed module, which is our iC-HS. And below it, there are two solder pads with through holes where you have to apply or to solder on your own laser diode. And then around our high-speed module, this little board in the middle, we have the bigger host adapter, which features all the easy-to-access pins for voltage supplies, the digital interface, input of our trigger signal, and of course output of the synchronization signal, so we can start our stopwatch. So this was the board itself. So we can go back now to the overall setup. The overall setup, the other things are then just in the back of it. There's the time-to-digital converter, programming adapters to connect everything to computer, and the sampling oscilloscope. To your right then, we have a photodiode connected also up to the needed parts. And last but not least, we have a graphical user interface that was programmed by our engineers. This shows the temporal pulse form from the oscilloscope. Currently, it shows a time range of 5,000 picoseconds full scale. And below it, we have the reading from the time-to-digital converter. At the beginning, I set this up that it is approximately 1 meter away from the laser source. So it now reads 3,380-90 picoseconds, which then translates to 100 centimeter in distance. And now, when I start to move this little photodiode, we can see that the pulse will begin to travel together with the distance that I make on the optical rail. We now have reached 2,000 picoseconds in time delay, about 60 centimeters away. And let's go for something that we can easily measure and see that it is a very practical distance. For example, 28, 29 centimeter. Now I set it to 30 centimeters. And this is very convenient for us here because we have a very good rule. And this is the A-sheet paper. This is about 30 centimeters in length. And as you can see, my 30 centimeter paper directly fills the gap between the photodiode and the laser diode behind the little lens here. And This shows about the range that we can go, and if I want to use my thumb as a rule of thumb to figure out how far we can move it and how accurate this is, if I go from those 30 centimeters and just move it by the width of my thumb, this reads then now 28 centimeters, which is 930 picoseconds. So this is quite the accuracy that we can reach with the setup. I would like now to go back to the presentation and continue with a bit of details how to configure this setup or the most important parts. So we, on the one hand, have the requirement, or we would like to have the requirement, that our laser pulse is displayed on the oscilloscope in a timely manner. So we need a repetition rate of our laser pulses fast enough that our sampling oscilloscope can sample it in less than a second, so we can pull out the data easily. The other requirement is that we would like to have an iSafe application here for our webinar. So it should be as low as possible. If we go for 100 kilohertz repetition rate with our oscillator, this is a good compromise for both those requirements. The iC-HS, in turn, is a more elaborate piece of device, and this is only as good as the configuration you apply to it. So for detecting it with a conventional photodiode, we need as much light or brightness as possible. So we just go for the 500 milliampere pulse current that it can deliver. Pulse length is, it should be easily visible on our oscilloscope screen, so that you as an audience can easily read it, but more important, it should be as short as possible so that we can make use of the gain switching effect and have, if you should build our design around the SPAD, have less ambiguity on this. So here we set it to 1,200 picoseconds electrical pulse length in the iC-HS, which yields a 200 picosecond light pulse. This is due to one physical effect in the laser diode itself. This is not an electronic artifact. It's just the turn-on delay that the laser diode needs to put out light, get into its stable state, and then send out the gain switching pulse. So the last piece where we need to consider our details of the setup is the time to digital converter, because it just has the stop signal and the start signal. It does not know if it's really hooked up well. So we need to compensate all the electronics and physical delays that happen in the setup. So this is the laser delay turn on, the propagation delay of the photodiode and all the other circuits that we or you may use, for example, amplifiers or comparators and such. And the third thing that we have to subtract from the reading from the time to digital converter are, of course, the wire length and the routings on the circuit boards. But for this, it's very handy to use the iC-HS sync delay, where you can just calibrate it. So this was my part of the demonstration. Let's go and give it back to Uwe. I hope I sparked your interest in this.
Very impressive. Thanks a lot, Stefan, for setting up this demonstration and explaining the selection criteria for all these key components. I'd like to summarize these again for the iC-HS. Why is the iC-HS so beneficial for these type of applications? Well, it enables ultra-short laser pulses required for this type of application with up to 500 milliamps of output current. It features a synchronization output to start the time-to-digital converter. It also features an energy limitation to support laser safety concepts. And all these functionalities, pulse duration, output current, synchronization output delay, energy limitation, are fully digitally controllable via SPI or I2C. Did we get you interested? Well, why not start right away working with the iC-HS? Get your starter kit right now. At the very least, you should have the high-speed module where you can put your laser diode on, the host adapter to easily operate the high-speed module, and the PC to SPI adapter to be able to use our graphical user interface to set up and operate the iC-HS. Check with a distributor near you or drop us a line at sales@ic-Haus.de. Thanks for attending, and back to you, Patrick, for the Q's and A's.
Thank you very much, Uwe. Thank you very much, Stefan. I think this was very interesting. We have a couple of questions here from the audience, so let's go through them now. The first question I have here, what is the maximum distance that can be achieved with iC-HS?
Yeah, maximum distance is achievable about 10 meters, we would say. That's a rough estimate. Highly depends on your effort that you're going to put into your sensor system.
Thank you. The next question is, what wavelength can be used or can be used?
We have two flavors of the iC-HS, the iC-HS or O2 and iC-HS O5 support red, visible red, near-infrared and infrared laser diodes, and the iC-HSB supports blue and direct green ones.
Okay, thank you. What is the best depth resolution that can be achieved?
Yeah, this is also limited by your time-to-digital converter. If you are not using it on a separate PCB, I believe you can go down to a few millimeters. But then if you want to go even better time resolutions, I would suggest you design something in silicon, because this is the limiting factor. How good can you measure the time you are traveling?
Okay, this was another part of the question. What are the contributing factors to this accuracy?
Yeah, for this mainly it's our comparator and the digital and analog circuitry that we need to evaluate the photo diode signal, because we start from a pulse, compare it to a reference voltage, and then make it to a differential signal, and this all adds up and adds quite some jitter. So in this easy setup with just off-the-shelf items, you only get 1 centimeter. But if you integrate this into one piece of silicon, should be one factor.
Great.
10 lower.
All right, next question. Does the chip support eye safety?
The chip itself, yes. Well, depends on what you design your setup for.
Eye safety is per se not a characteristic of a single device. It's a concept. But the iC-HS supports such eye safety concepts in two ways. First, as Stefan explained, we're using a very low duty cycle here, which makes the average power quite low, way below the requirement for class 1, for instance. Secondly, we have the energy limitation feature, which helps to further keep the laser output extremely low, even in failure condition.
Great. Okay. All right, we got a lot of questions here coming in. The next one, should a classical edge emitter diode be used or should I use the VCSEL?
Well, this is up to you.
Okay.
Though it is often claimed that those short cavity emitters like VCSELs would not emit the gain switching spike, this is simply not true. Our experience is that both edge emitters or VCSELs emit this gain switching spike which we're using in this application.
And also might be you can really check your turn on delay of each your different laser diodes. Maybe this is also an advantage if you want faster response times and even a shorter duty cycle on the iC-HS.
Okay. Next one. What considerations are important for PCB layout?
Well, those signals are fast. So your routings should apply all means that you have to have it on a short length, obviously, and no sharp edges, exact length for the positive and the negative signal. We are dealing here really with picoseconds, and this is not something that all of the PCB designers take into account when you just let them route them automatically.
All right. Okay, next question. Does the LD turn-on delay need to be calibrated individually for each device?
I would say if you want to go to the really, really small distances, sub-centimeter, you should do it. If you are good enough with plus or minus 1 or 2 centimeters, you can get it from like the batch information of a diode.
Okay, very good. Next one. Can pulse patterns be sent?
Not inherently from the iC-HS, but if you apply us our iC-HS a trigger signal, which is a pulse pattern, because the iC-HS only looks at the rising edge of the inputted trigger pulse, you can make your own pattern.
For the sake of simplicity, we're just using a free-running oscillator here for the trigger signal. But since the iC-HS more or less operates transparently, so it outputs a laser pulse for each pulse you input at the trigger input. So if you want to generate pulse patterns, sure, go ahead.
Very good. Okay, still more questions. Will the webinar be available for download or stream? Yes, it will be. So this question is answered. Do you have reference design or guidelines for tuning the laser diode poles rise and fall using shunt components, etc.?
No, not that I'm aware of.
A shunt component might be used to speed up the falling edge, but that's about it. So currently we do not support explicit application notes or design guidelines along this line.
Okay. So I think we still have a bit of time. All right, let's go on. Can the modules be connected in parallel to reach, for example, 2 amps with 4 iC-HS 05?
In theory, yes, because the outputs operate as current sources, and you can easily parallel current sources, but you'll probably be dealing with different propagation delays, have to control 4 different drivers. I would not recommend that.
Okay. All right. Is reflected light also recognizable, or does the target need to be a silicon SPA diode or SPA diode?
well, it is detectable for sure. We just went the easy route by adding one little, focusing lens in front of our normal photodiode. But if you go not for this little 2 millimeter diameter lens, but use a bigger one, you sure can collect enough light and then focus it on the normal diode and then go for a reflective setup. But we are an electronics company and not an optics company.
To be honest, the reflective setup would be the commonly used setup where you have the laser source and the spat in the same plane, and then detecting the reflected light from your target. But as Stefan explained, for the sake of simplicity, we chose for the demonstration setup this one-way measurement.
All right. And one last question. Can the lasers be pre-glowed?
Not by means of the driver itself, plus it would quench the gain switching spike. Preload, I guess, is it is meant biasing, so applying a bias current close to the laser threshold, but this would quench and disable the gain switching spike, which we use here in this application.
Okay, thank you very much. So I have no more question here now. Should there be any questions that have not been answered right now, don't worry. Our expert will answer them later on per email. This concludes the Q&A session. One last thing, iC-Haus is going to be present this year at the SPS and Electronica show. So we're looking forward to meeting you there and have some interesting discussions in person again. Okay, this was it for our webinar today. I hope you enjoyed it and it was interesting for you. Thank you very much for your attendance and goodbye.
Bye.
Goodbye.
iC-Haus. Integrated circuits.